Hello everyone, welcome back. In the previous video we talked about the free-h command. We broke down the famous buffer cache column and I showed you most of the numbers reported by free actually come from a single file, which is proc meminfo. Let me type it here. Cat proc meminfo. So um, as I said, every information you have in free-h was coming from this file. And to be honest, to keep the video focused, I intentionally simplified a few things. Today, I want to revisit some of those topics and explain them in more detail. We are going to answer some questions. And yeah, let's get started. So, as I said, everything we discussed in the previous video come from here. As you can see, let me type first free-k first, then let's go back to mem.info. We talked about this column and we took our time explaining it, and we said that it is basically the cache D plus the buffer, which is here. In this case, we have 0 plus something called the slab reclaimable. And let me look at this test environment, cloud user. Okay, so the SU, let's see some of the stuff here. Proc meminfo. As I said, but to be honest, I didn't mention something that I think it's very important to know that these actually command are going to show you only the system-wide information. What does that mean? That means that this command actually is not going to let you know how this memory is distributed, for example, in a NUMA node, how it is distributed in containers or cgroups. For many workload, that's very normal. It's perfectly fine. But on larger server, the distinction become extremely important. So I want to give you just a hint or just an overview about what NUMA node is. So if there is someone that doesn't know what NUMA node is, he can at least have a at least have he can at least understand what I was talking about here in this video. So I just grabbed this picture here. Let me show you. Okay, maybe make it more bigger. So in NUMA actually stand for non-uniform memory access. Modern server often have multiple CPU sockets. As you can see here, we have four. Okay, four CPU socket, and each socket has memory physically attached to it. Usually like this, for example, let's take this CPU 0. You'll find out that CPU 0 is actually connected to memory through memory controller and through something called channels. Maybe we can talk about it in detail in another video, but today we are going to just learn the basics. So, and the CPU, if there is no node affinity or any policies that is configured or tuned on the server, you can access actually from the CPU. Let's say this is a process. This process can access actually the memory, the local memory here, and it also could access any other memory that it touched to any other CPU, like this one, for example. But the cost of course, of allocating memory or taking some data from the local memory is going to be way less than connecting to other CPU's memory because of this, what we called here, as you can see, the interconnect. Because you have this interconnect is going to be the bottleneck for your workload. Okay, so As I was saying, Linux is going to group each CPU and its local memory into what we call the NUMA node. Accessing local memory is, of course, going to be faster than accessing memory attached to another NUMA node. That's why Linux try to keep the process close to their memory whenever possible. And you should also do that as much as possible. You have to think about it, to think about your workload, if it is going to fit in your local memory or not. Because if you, let's say this is a 8 gig and 8 gig, and you are trying to allocate in your physical memory more than 8 gig, is not going to be, it's not, that means it's not fit into your memory, so you're going to look for uh, what we call the throughput. Yeah, the throughput. So you are looking for the throughput, not for the latency in this case. So you have to think about it. There is the pros and cons, of course. We might talk about this later. Okay, but in this video, this is all what we need to know about the NUMA node. Maybe we can raise some cases here. Like, okay, there is one case I want to mention here. Let's say, uh, imagine a server like this one, have 4 NUMA node. By the way, as we said, that the Linux try to group the CPUs and local memory to what called NUMA node. So to us, this is a NUMA node. This is also, and this one also, etc. So we have here 4 NUMA node. Okay, but as I was saying, for example, let's see, I want to remind you about something. Let's say syscontrol -a, and we grab for, let's say, I think mem3. Okay, and we have here, it's only 67 megabyte. No, it's yeah, 67 megabyte. So this, let's say it is, to make it easier for us, let's say it is it is 80 megabyte, 80 megabyte. What we called, this is what we call the watermark to us. So what does this mean? It means that your system can't have less than this number. This number should be free always, because the OS is going to use it anyway, and actually the TCP/IP stack is going to be part of that min free. It's going to use that part of the min free. Okay, but let's go back here. As I was saying, imagine you have this 80 megabytes. So what you're going to do, the system, when you put this number in the min free, is going to, let's say, divide it by 4. It's not exactly dividing it, but I'm trying to simplify it here. So each NUMA node should be at least have 20 megabyte here, 20 megabyte. When you reach this 20 megabyte, the system, the keyswap D, by the way, keyswap-D is NUMA node aware. So you have, in this case, you're gonna have keyswap-D 0, 1, 2, 3, and each one is responsible for one node. Okay, for example, this one is going to be triggered. As we said, there is 2 parameters. The first one is going to be the watermark, and the second one is going to be the ratio, which is by default 30 millisecond. 30, yeah, 30 millisecond. Okay, this keyswap-D is going to be wakes up, triggered, and is going to start to claim some some data. As we said, let's say, for example, here we have some anonymous pages. Let's say this part is just anonymous pages. So you're going to start swapping. Okay, you're going to start swapping here, but in the same time, in this node, you still have, let's say, 4 gig, and this one you have 6 gig, and this one you have 8 gig, or whatever. You have 8 gig free. So when you look at free-h, you'll see that you still have 18 gig or more, almost more than 18 gig free. So you won't be able, if you are if you base your conclusion from the free command, you'll see that you still have 18 gigs still free. But at the same time, when you do, for example, as I said, free-h shows you that you are good, but when you check, for example, sar-b1, okay, this one sar is not installed. Sorry for that. sar-b1. So you'll see here that your system is swapping. Okay. So as I was saying, you still have a total amount of free memory across all nodes. Everything looks healthy, but that doesn't mean every NUMA node is healthy. So if a workload is restricted to node 0, for example, as we were describing it here, then, for example, because of its CPU affinity or memory policy, it can experience memory pressure, reclaim, or even swapping. Let's say we have here anonymous pages. Anonymous pages should be swapped. As I said, you start from slab reclaimable. The slab reclaimable, you just discard it. And also after that, it's going to inactive file. After inactive file is going to let's see it here. Let's take it here. So just as a reminder, maybe to refresh your memory, let's take it here. Okay. So what your system is going to do is going to start as a beginning from this lab reclaimable. First one. Second one is going to be the inactive files. This one. Then the active file, let's say 3. This one is going to be discarded. Those two also are going to be discarded because you already have them in the disk. So you don't have to push them anywhere. So the system just discard those files. Also, after that, you're going to check the inactive anonymous. Well, where is it? Yeah, the inactive anonymous. This one is going to be the 4th. The active anonymous is going to be the 5th. But those one are going to be swapped. Are going to the swap. Okay. That's why most of the time to configure your swap, you need to be aware of how your anonymous pages, how much do you have, and how it is behaving. Okay, so your swapping is going to be based on the anonymous pages. And at the end, when the system is not able, or the OS or the kernel is not able to reclaim enough memory, then you're going to use OOM to kill uh, the to kill a process or multi processes based on something called badness or score or OOM score. Let me show you here. For example, if we check any application, let's see what I have here. For example, cat etc password. Let me see my application. Okay, do I have it? Is it working here? Yeah. Gradient C. Okay, this is good. Cat proc. Let's see this one. If I go to score, it's going to give me how much the system is given this process a number, and this number is going to be the more the higher the number is, the more this process is going to be a victim to the OOM killer. Okay, but if you don't want, for example, this DMC service or your HTTP proxy, your Nginx, to be killed, and you want to give it a priority, what you should do, you can go here to proc the same. Let me use the same command, and there is something called adjust. Okay, and you give it, for example, minus 17. It's not a rule to give it minus 17. You just have to give it a lower number. You can, for example, give it minus 100 or minus 1000. Just a habit. I use minus 17. There is no reason behind it. Okay. So let's go back here. Um, when I was talking about the NUMA node, the NUMA node here. Okay. So as I was saying, so in this case, when you have, as I was saying, let's say here we said that this one is reaching its limit, but those are still free. In this case, the free dash h does not give you any idea what you are facing, and you might be confused or you might not understand what's really happening in your system. So that's why myself I did created this script actually using memstat dash this script. I might share it in the I might also share it with you in the in the description if you like it. This is going to show me, because you see the limitation in free dash h is not showing me the dirty, is not giving me any idea how much anonymous I have, the slab how big it is, because I want my slab to go so big and my system gets slower. Also, there is something called hit and miss. Let me show you what does this mean, because it seems not intuitive at first. But when you have a process here, and this process is using the memory, but there is no affinity, no limitation here. So this process is going to first use local memory, but sometimes it's not going to be able to allocate any memory from here for some reason. Maybe it is full. Then what's going to happen? Maybe there is another process that, because there is a concept called the first touch. We'll talk about it also. And the first touch, when once let's say this process here allocate some memory, is going to reserve the memory, but it's not going to take any actually physical memory to back it up. But what's going to happen? Let's say there is another. This is multi-process service. There is another process here. Start to touch that memory that is has been allocated by this process or by this thread, for example. What's going to happen? The CPU or the OS is going to allocate the memory here. So when you try to access that memory from this node, what's going to happen? You are going through this what it called uh, this channel. Okay, so this one is going to be through the interconnect, and the problem is that the interconnect is way slower than the memory channel that is here. So it's going to be way slower than the local memory. So when it is using the local memory that called hit, when it is using the foreign memory that's called miss. Okay, that's what I'm doing here in this script. So that's, and because I only have one NUMA node, you can see only here I have NUMA node 0. But if there is more than one NUMA node, of course, and there is memory pressure, you'll see there is some misses. But here it's basically 100% hit. Okay, This lab we already talked about it. It's just the entry and the inode, etc., and the buffer head. And the anonymous is the files that are not backed up in the disk. The dirty are just the files that were clean, but something happened and the process modified them, so they are not the same as they are in the disk. So we have to flush them in the disk. Okay, and in this script, I only use actually files that already existed in the system. Let me show you. For example, sys devices system node, and if I tap twice you see that I only have node 0 because this is actually a virtual machine. I only have one NUMA node, but if I have multiple NUMA node, of course in the this script you see for 0 1 2 3 etc., but in this case we don't have it. Meminfo, sorry, node 0 meminfo. So it is basically the same file, but this one it's a bit different. This one is by NUMA node. As you can see, node 0 here, we have total memory, etc. Okay. Also, I'm using this file by the script vmstat, and I have used the numastat file. This one. This one, I gathered the miss and hit from this one to create the script. I'll share it, as I said in the description. If you like it, you can download it and use it. So there is one thing actually. Let me show you here. For example, I have this quadlet, which is a bit weird from as I said, I'm not a big fan of free DH, but I use it, to be honest, out of habit, and just to get it gives me a general idea what I have. But if there is a problem, it's not going to give me what I need. Of course. Okay, so let me where I was. Yeah, I was saying that there is something weird with free-age. Let me show you here. Podman exec dash it. Let's see this pod. This is just a quadlet. The good thing about quadlet for me, I only use it by using the pod. If my application skill, I can just take it and push it on into a deployment or uh, or what. Yeah, so it's going to be easier to scale. This is one of the things why I love Quadlet. But yeah, let's move on. Let's use bash. So free dash h. When you look at free dash h inside the container, you're seeing actually something bit weird. You are seeing the system-wide data. So it's not just the pod. Okay, that's why it might show you, as I said, the overall memory information depending on the kernel, of course, and cgroup version, and the tools available inside the container. But usually it's not going to work for you. It's not going to show you container wide. That's what I mean. Okay, a container might only be allowed to use 2 GB of memory, even though the host has 128 gigabyte instead. When troubleshooting containers, always remember that the container's memory limit, it's often more important than the host local memory. Okay, so if memory pressure becomes too high, let's say, for example, well, let's say you have a Kubernetes cluster. I don't have actually access to any cluster right now, but just so you know, when you have a Kubernetes cluster and you are reaching the limit, and OOM are going to be triggered any moment. If the kubelet was faster, of course, kubelet is going to stop the pod and move the pod to another node. depending, of course, on the what it called in the schedule and the policy you are using. But if the OOM was faster, of course, OOM is going to kill that pod, and you might see this happen many times before kubelet actually move that pod. So it might cause an issue here. So I think about the last video. I think now we cover what we don't well what we didn't mention and we didn't cover because of the time being. I want to move from here to something might help us all also in the next videos, which is the Linux application memory and the virtual memory. In this part, I want to talk about how application use memory and how to profile application memory usage. It introduced, I mean, this part, the operating system memory management concept, including demand and paging, trimming, and swapping as a foundation for more advanced virtual memory topics covered in this series. So I want to start actually with the demand pages and what it means. Let me open, for example, Paint here. Okay, so we talked about it earlier, but we didn't take our times. So sometimes here, let's say, okay, let's say there is a process here. And as I said, this process, for example, you configure this process to use, let's say 8 gig. Okay, actually, the process is not going to the system, sorry, the system, let's say the OS is not going to give the process this 8 gig immediately. What's going to happen? There is something called first reservation. Let's say this is going to happen first. What's reservation is actually just a virtual memory. The process think that it is actually on that 8 gig. The OS just promising the process, I promise you, I'm going to give you that 8 gig, and the process is going to believe the OS. So that's in general what happened. But when the process start, as I said, touching or zeroing the array or something, what's going to happen? The OS is going to allocate the second phase called allocation. Allocation. Okay. Allocation means that right now you have the physical mapped to the virtual memory. The physical memory mapped to the virtual memory. So this is in general what really happened. But I want to start from before this. I want to start from the beginning. I want to show you something. Let's say we have, maybe we'll go back to this. Let's say you have a box here and you have another box here. Okay, this is terrible. Let's say both those, imagine those two are the same size. Okay, so if you divide this to 4 and you divide this to 8, okay, how many pointer you are going to need to point to each part of this box? Here you're going to need just 4 pointer, but here you need 8 pointer. You say this is simple. Of course it's simple, but we are trying to simplify it here, etc. Okay, so now imagine you have 64 gig of RAM, and of course, let's say 1 kilobyte, just to 10 byte. 1 megabyte is 2 to the 20, and 1 gig is 2 to the 30. Okay, so if you want, for example, to divide this RAM by 4K, which is usually the default, how much you think you're gonna have a page here? You're gonna have 64, as we said, multiple 2 to the 30 divided by 4 2 to the 10, you'll end up with almost 17 million. But if you divide it by a huge pages, which is 2 megabyte, you see 2 multiple 2 to the 20. You'll end up with almost 32,000 pages. We're talking about pages here. Why I'm talking about this? Because sometimes, let's go back now to what we were talking about. Okay, let's say the processor, this is a CPU, okay, and the process want to write to the memory. So what's really happened on the CPU? There is a cache, a chip inside the CPU here. Let's say this one called TLB. What TLB is? Translation look aside buffer. When you look inside the TLB, you find only virtual memory to physical memory translation. So let's say it's read this one exist, this one it find invalid, which means it doesn't have the information. So when you say the CPU actually in this case is going to uh, the CPU in this case when this is invalid is going to raise an exception, do fault page. What does that mean? The OS is going to take control in this case, and the OS there is in the CPU there is something, another chip called MMU. This MMU is actually behind the CPU. This is part of the CPU. Let's say it is responsible to do a page walk. What does that mean? Let's say this is the memory. The MMU is going to do a page walk here to check something in the memory. Let's take this part here to understand what's really happened. So there is something like, let's say another small table called PGD. The PGD mean page global directory. It's just a number of pointer. Let's say there is a pointer here, which is the last pointer, pointing to something else called PUD. The PUD is actually a page upper directory. It's basically another table. And the last one also pointing to something called PMD, the middle directory. The middle directory is pointing to something else called the PTE. The PTE is pointing to the physical table. This is how the MMU actually calculate and do the translation from the virtual memory to the physical memory. How this is done? So imagine you have 4K. So as we said before, you're going to need more pointer than when you divide it to 2 megabyte pages, of course. So you're going to need to work all this PGD, PUD, PMD, and PTE to find the final answer and find the page that you want to point to, and the OS is going to give it back to load it in the TLB. So now this one is not invalid. Now you have the pointer. But imagine your system is using a lot of pages, your process is using a lot of pages. You allocate a lot of memory, and you read, write, read, write, read, write. What's going to happen here? This because this is a very limited resources, this is going to be filled. Okay, and then what you're going to do, you're going to start flush some data to load another data. Okay, then it's going back, then forth, go back, forth, go back, forth. Now you have a lot of TLB misses. So what people usually do, they move from 4 kilobyte to 2 megabyte. So right now you're not going, so it costs less, of course, to calculate the final destination, but in the same time you're gonna need the less entries in the TLB. For example, in 2 megabyte, you're gonna calculate from PGD to PUD, from PUD to PMD, but here you're not going to PTE, you're directly pointing to the physical memory. So now you have less step, you have one less step. Okay. Sometimes also people, when they are using 1 gigabyte of memory as page, you're not going to use the PMD. From the PUD directly is going to connect to the physical or the last destination here. So way less bulk through the page table. I hope you understand this part. So let's move on. I want to show you something. I want to show you the process virtual memory so we can complete the picture. Let's say this is a process, and you're gonna have here something called text, something here called data. Here usually going to have something called heap, and here sometimes, so at least you're gonna have three parts, but sometimes you're going to have, for example, shared memory. Shared memory actually is like the shemam and the IPC. We talked about it in the last video. So the data, the text is just contain the executable binary code, key properties, shared across all instances of the same program, only one copy in memory, which means that if you have multiple processes, and let's say this is the memory, usually this is going to be shared. For example, let's say you load from the disk. The disk should be way bigger, but yeah, you load from the disk here to the memory. If you have another process here, the same text, the same pointer to the text is going to point to the same page, okay, or pages. So as I said, it is read only. The kernel enforces this, modify only by exec, which load a new binary. If physical memory is exhausted and the page cache is trimmed, the executable may evicted and later reread from the file system. As we said, actually, this is called the active or inactive file or clean file. The system, if there is a memory pressure, the system is just going to trip or discard this part because you already have it in the disk. So it's just going to be to discard it. It's not going to be swapped. Okay. So, and we have also the data. the data contain per process data key property. It is actually unique per process. Thread created via clone can share it. You can, if you have multi-threaded processes, the data could be shared between those as the text also that could be shared by for the threads. And it is actually read write. Okay, and actually there is two types. There is the BSS, which is uninitialized static data, and there is the heap. Okay, the heap grow via malloc, as we talked about it when you use malloc. When you, actually, this one is not the heap. It's the stack. We'll talk about it. The stack. Okay, this one. This was a mistake. Sorry. This is actually the stack. Okay. This is the stack. Huh. Okay. This is the stack. Okay. So as I said, the data is there is two types. There is the .bss and there is the heap. The heap is grow via malloc. Malloc, what it's going to do? By the way, this is called VMA, and this is called VMA. This is VMA. This is another VMA. Okay. So when you do malloc, for example, as you know, let's say this is the heap, and there is a pointer here was by Asberg by Asberg. Okay, when you do allocate another memory, Asberg is just going to be take another upper value here. Let's say Asberg is a point to upper value to be here. But this is only virtual memory. Just remember, this is we are talking here about virtual memory because the OS is trying to organize the VMA here. So when you the pointer become here, when the process start touching the memory, what's going to happen? The uh, OS is going to back up the reservation by a physical allocation. It's going to give you the memory that you are asking for. When you do free, just remember this is, let's say, part of the heap. Let's say this is the heap. Okay, let's say it is contiguous and everything is looking fine here. Let's say this is the heap. Okay, and the process is starting to free by using free. Let's see it here. For example, when you do man malloc, let's look for free. As it is saying, the free function, the memory space pointed to by pointer, which must have been returned by a previous all to malloc, etc. Actually, this is not what I want. I want this allocation size byte and return the pointer to the allocated memory. Yeah, exactly this one. What does this mean? Actually, what's going to happen when you do a free, because usually after malloc, we might use free. Let's say this function was going to happen. The pointer is going to be reduced, for example, to here. So this part, actually, if the memory is not going to be released from the physical memory, just here, you're going to have a flag saying that this one is reusable. Okay, so whenever the process is trying to, let's say the process free this part, then there is another malloc and trying to use that part of the memory, you can rewrite on this part of the memory. But the free is not going to release this part. Okay, so now we are talking about this the stack. The stack, when actually used by the OS, when you jump in from one subroutine to another, there is pointer and register, etc., is going to be pushed here to the stack. There is a command actually to you can check the stack, but let me show you just the file that this command is using and how, for example, let's say let's say here, cat when you do proc. If you can see, when you jump here, you read it like a pile. When you jump from one subroutine to another, you push the previous one on the stack, etc., etc. Okay, this is the stack. When you have, let's go back here. Maybe we should, yeah, there is no, let's say this is the process, as we said, and we have here the text, we have here the data, and we have here the stack. The stack actually, when you have multi-threaded process, multiple thread in the same process, what's going to happen? Of course, they share the same text, they share the same data, but they are going to have different stack. Let's say this for thread 1 and this is for thread 2, because all the local, for example, this thread is on function 1 and this one is on function 2. So here you're going to have different variable, different local variable for this thread, etc. is going to be stored here. Let's say sometime you have a deep array, or you have, let's say, recurs in the same function, and you are seeing some issues in your application. Please check this limitation what you have in the stack size. Sometimes, because in the default is 8 megabyte, but sometimes your application need more, you need to tune this value. Okay, so I think we talk about this one. Let's see, we talk about sometimes you're going to have the shared memory, the shemam. As we said, the shemam is just inside the proc, the dev shemam. Those are not just for your information. Those are actually not real files. Those are not backed by the disk. That's what I mean, not real file. So those are in memory file. It's not in the file system. Okay, in the TMPFS file system. Okay, and there is also the IPCS command. This is going to show you, for example, the inter-process connection between these processes. And you have, for example, 56 are attached to 6 processes, and there is this 848. There is only one is using it right now, etc. So those are the shared memories here. Um, this is what we were saying when we talk about demand and demand patience. So the system is not going to give you immediately the RAM that you need, but is going to give you as much as you as much as is going to give you what you have touched by your process. For example, you in Java application you have XMX, let's say 80 gig. You're not going to get the OS is not going to give you the 80 gig. It's going to give you, let's say, 1 gig. Whenever your process is touching more, it's going to give you more, etc. So um, I want to talk about another thing. Since we are here, I want to talk about the difference between minor fault and major fault. actually, major fault. The minor fault pages, minor page fault, the virtual address is valid, but the physical mapping is not yet in the TLB. This is minor. Sorry, this is minor, yeah. So when you do SAR here, just so this one doesn't have SAR, so when you do SAR dash B1, you'll see that's why I was talking all this talk, just so when we see those numbers, we understand what you are facing. When you see minor fault, this one is minor fault, is basically what it means. Usually not 100%, if because sometimes you have fault and you have major fault. This that's mean because the minor fault including also the major fault. So as I said, the minor fault, that's mean your virtual address is valid, but the physical mapping is not yet in the TLB, what we are talking about before. But the major fault, the page must be fetched from the the storage. Either it is swapped or you were just getting your binary or your text from the disk. Okay. Uh, I think we talk about the process, the virtual memory. So maybe we talk about just one thing here, just to complete the picture. When you have fork this process, let's say this process, there is no thread here. Let's say this process, and you do fork. When you fork a process, the child inherit the parent pages table, and let me show you. Let's say here you have this part is the parent memory. So when you fork it, you fork this process, you're gonna have another process here, let's say P2, have the same virtual memory, and they all pointing to the same physical memory. Okay, so what's going to change? Uh, this is called copy on write. Actually, the child, as I said, inherit the parent page table entries, pointers to the same physical pages. Neither parent nor child immediately get a new physical pages. This is called the copy on write. On the first write by either process to a shared pages, to a shared page, the kernel allocate a new page and copy the content. That means that when this or this start to modify something here, then the system start copy that part. Okay, so now you'll see, for example, this is pointing here instead of here. This is called cow. Okay. I think that's it for today. Let's hope I didn't forget anything. So I hope this was helpful for you, and I hope we can move from here to start do some labs and we test some things. And if you like the video, please give me a thumbs up, share the video. We want this community to become bigger, and maybe you can do something based from my videos, and you can share it. If you have a question, please ask me. I will try to answer it. And thank you guys. Thank you. Bye.